Superblack materials abound, and they are surprisingly useful. But most superblack coatings are made from fancy nanotubes. I definitely did not expect to see superblack wood. Black as an achromatic color is the absence or absorption of visible light, right? But nothing on Earth completely absorbs all light. I mean, sometimes I grab a black shirt and some black pants, and one of them is a really obviously blacker black than the other. That is, it is absorbing more light and possibly more laundry bleach. Superblack materials absorb more light than most. Where standard black paint absorbs 97.5% of light, superblack absorbs 99% or more. You may have heard stories of Vantablack, a superblack coating created by chemical vapor deposition of vertically aligned nanotube arrays. That's where the Vanta part comes from. More specifically, artist Anish Kapoor was licensed exclusive use of Vantablack for artistic purposes. This in turn annoyed artist Stuart Semple, who went on to invent Black 2.0 and ultimately 3.0, which are, quote, for the benefit of all artists. Except Anish Kapoor. Admittedly, Semple's paint is less superblack than Vantablack is, but it is more spiteful, and that gives it some points in my book. But as much as superblack inspires artists, these light-absorptive coatings have tons of functional applications as well. For example, astronomy. You see how the inside of this telescope here is black? That prevents light from bouncing around and becoming as much of a source of noise, and the fancier your optics, the more you want to reduce stray radiation and enhance your scope's sensitivity. That's just one use case, but there are lots of scenarios where you want to maximize light absorption. Solar steam generation and desalination, solar panels, weird stealth tech I don't have the clearance to know about. Nature even produces some hyper-low reflectance materials. The male bird of paradise has feathers whose structures absorb up to 99.95% of light, which, by the way, makes them an absolutely terrifying void when viewed from another angle during their mating display. But I guess that's what female birds of paradise are into, and frankly, who am I to judge? Like the blues of a peacock, the superblack of that little void bird's feathers are produced by structural coloration. Rather than pigment, the color is produced by microscopic structures in their feathers that interfere with light waves. With peacock's blue feathers, only blue frequencies escape. And it's likewise with human synthesized superblacks. They're typically made from a forest of carbon nanotubes that light wanders into and, like children in a German fairy tale, never return. And that was, I cannot overstate this, nothing to do with the intent of these authors when this week's story started out. Our researchers were initially working on a totally different do weird things with high energy plasma and wood project because they are forestry researchers and they are scholars of doing cool things with trees and wood. Specifically, they were trying to use plasma to make wood more water repellent, which, by the way, apparently is a thing that can be done. You can apply plasma energy to wood to make it more water repellent, although most of the existing examples also layered a thin film of fluoropolymer on top. But they were experimenting with techniques to apply plasma energy to refine this whole waterproof wood thing. And as they were doing so, they noticed something strange. When heating the wood, the longitudinal surfaces, the long grain that you see here, got a bit darker when exposed to progressively higher plasma energy levels. On the other hand, the transverse end, like the cut end, when that was exposed to the same high energy plasma, it became extremely dark, then black. Yeah, super black. At this point, our researchers drop the waterproofing project because, again, They're forestry researchers, and they've found a cool thing they can do with wood and high-energy plasma, so this is still totally on task for them. They send this wood off to have its reflectance measured because, well, their lab's built to do cool things with wood and high-energy plasma. They were not expecting to measure light reflectance and don't have that equipment. But when the results come back, overall, we're looking at a solid performance from Nixalon. Their name, Nix like night and Xylon like the Greek word for wood. And it outperforms options like black aluminum and even sheeting made of vertically aligned carbon fibers, the Flock 55 that you see here. Overall, the plasma-treated wood absorbed 99.32% of visible light, which is in the ballpark of the void bird of paradise we saw earlier. It's still outperformed by top performers in Superblack. MIT's carbon nanotube on aluminum design still comes in at 99.995% absorption. Though, interestingly, they also happened to find their Superblack while working on a totally different project. But hey, we've got wood and some plasma, not microfabricated nanotubes, so that this technique even brings you into the Superblack range is pretty cool. Now, obviously the idea of carbonizing wood to blacken it is nothing new. You can blacken wood by putting it on a hot plate. But, as we said at the beginning, Superblack is more than just really quite black. And the structural coloration we talked about, whether with forests of nanotubes or the structure of a void bird's feathers, is surprisingly similar to what's going on with the plasma-treated wood. This is a super close-up microscopic view of that cut grain of white pine, the side of the wood that gets super black. On the top, you see untreated wood. The little holes in it are called tracheids. Tracheids are these long, tube-like lignified cells that go up the stem of a plant or the trunk of a tree. Those are part of the plant's water transport system, and because they are rich in lignin, they also provide structural support to the plant's stem or trunk. So when we look at the cut grain of wood, we're getting like a cross-section of these tubes that were once part of the trunk of the tree. Now, as you see on the bottom row of images, plasma treatment changes the shape of these structures. Wood is made up of a bunch of different organic chemicals, and plasma degrades the various polymers in the wood differently, leaving lignin-rich remnants and creating voids in these little tracheid cells, which ultimately trap light to create the super black effect. The researchers used white pine in those microscopy images, but most of the studies here were done using basswood, so we're apparently talking about a fairly available wood species. So why is that important? Well, because when you've succeeded at your do cool things with high energy plasma and wood project, you gotta turn around and ask, what can it be used for? Well, a lot may depend on how efficient its manufacturer will ultimately be. I mean, NASA is going to go for the absolute blackest black ever to exist for their space telescopes, sure, but not everything needs NASA-grade super black, and if it can be feasibly used in some commercial or consumer applications instead of things like black aluminum, well, as we saw here, you'd clearly get a more effective result. But the authors make a really interesting point in the discussion of their paper. This plasma-treated super black wood isn't just competing with other black materials like black aluminum and Flock 55. The plasma-treated super black wood is also competing with other woods. There is intense global demand for black wood, and as a result, most of those tree species, including ebony, African blackwood, and many rosewood species, are threatened or endangered from overharvesting. I mentioned before that this technique worked with fairly available wood species. That is to say, species that are in no way vulnerable or endangered. It would be cool if we could use wood for super black applications, but I think it would be really cool if it could also take some pressure off of threatened and endangered species of trees by providing black wood for consumer goods in a more ecologically sustainable way. So, what I've learned from this is, yes, plasma treating wood can make microscopic microscopic changes to its structure that allow the cut grain to reflect incredibly little light. And hopefully, that this could be used both for applications where that low reflectance is useful and maybe to get a more sustainable source of blackwood. But really, what I've learned from this is we've got to let forestry researchers play with plasma more. It really pays off. Let them play with plasma. What could go wrong?